Hey there, everyone. Welcome to my data science channel. My name is Ryan Schul. I talk about all kinds of data science topics, machine learning, artificial intelligence, and so on and so forth. So in today's project, I want to show you how to do time series analysis, and we're going to look at a bunch of time series models, and we're going to loop through all of these models because basically I'm kind of a lazy person. I don't want to test a whole bunch of models independently and maybe make a bad decision because I didn't test a model that I should have tested, and one model can outperform another model, but I didn't know about that and you didn't know about that either. So now we're using a model that is subpar on the data set that we are analyzing. Okay. And this basically totally makes sense because different models make different assumptions about the data. So the important or one of the most important things you can do is test a whole bunch of different models on your data because you can't expect one specific model is going to outperform the others when you haven't even tested that. You can't make these assumptions, right? You don't know if ARIMA is best, SARIMA, Holt Winters, LSTM, XGBoost, Naive Bayes. You don't know which one is best until you test it and you see what the outcome is. Then you can understand the predictive power of that model based on the R score that the model generates. And the R score is the goodness of fit between the different data points. If you think about all the X um, on the X coordinate going left to right or right to left, and the Y coordinates going up and down vertical position. You can see the distribution of data points can be up, down, all around. It can loop around in many different directions, but you don't know what that is until you run the model and see how it performs, okay? So an R squared closer to 1.0 is better. 0 means the model is not able to make any decision whatsoever, and sometimes we can actually get a negative R squared. It sounds weird, but that can happen. And the model is actually giving you the wrong information or bad information. It's not adding any value whatsoever, and that's okay. But if you see that kind of scenario, you have to pick a different model and test it. So let me go ahead and load the data right here. So Control Enter to run, and I have temperature monitoring. So I found this on the New York City website. I have the link at the bottom here, bottom of the notebook. So this came from here, data, City of New York, data sets, temperature monitoring. And I think I was originally looking at air quality around New York City, and I just landed on this one. So my original search was more like air quality, but then I pivoted a little bit and got this instead. Okay, and again, so any kind of time series analysis is based on a change in some type of pattern over a period of time. So it can be air quality, air temperature, it can be a stock price, it can be um, anything that happens given a certain period of time. That's all it is. So time series is measuring things based on time. So if we go over here, I loaded the data. I have 50,000 records. And by the way, I'm taking 50,000 of the original shape. If I go over here, temp monitoring.csv, this is on my desktop. So if I go over here, where is this thing? Personality assessment. No, that's not it. So if I go over here, temp monitoring. So 174 meg. So kind of a big file. I think they had like 500,000 or something like that records in the file. Let me open it and see real quick. This is pretty fast. Okay. So originally we had way more than 50K, but I truncated it to 50K just to make the model run faster. The only reason I'm doing that is just to make things go a little bit quicker here. Oh, it's opening now, so it is a little bit slow. My laptop is slow, guys, so just bear with it. Okay, so I'm going to go ahead and convert everything to date time. So anything it's hour units of hours, that's how the data is coming into us. And any kind of day, I'm going to create a timestamp based on the day and the hours throughout the day. And I'm going to set that as my time series. So over here, I have time series frequency H. So this is hourly. This is how the data comes in. So that totally makes sense to me. But it really depends on your scenario and the actual data that you're trying to analyze. If you're getting monthly data, then you're analyzing monthly, right? Your frequency is monthly, weekly is weekly, daily is daily, hour is hour. You could have minute data, you can have real-time data, right? This data is too large to fit into Excel. So if I go over here, I'm just wanting to give you a quick view of this thing. It doesn't even load up the whole thing. It's pretty big. So we have the day and the hour, right? Going back to 2018, and this gets truncated. Well, this is really truncated. So 6:15 to 9:15, and you have records for every hour. So it's a pretty big data set. Okay, that's the point. So I want to analyze the entire data set. I'm just going to take the first 50,000 records. That's what I'm taking head of 50 right here. And I'm looking at hour frequency. So frequency equals hour. So it is important to set your time series to the specific frequency that you're looking at. And I'm looking at a rolling mean of 3 periods. So this is 3 hours, right? So if you're looking at days, it's 3 days. If you're looking at months, it's 3 months. If you're looking at hours, obviously it's 3 hours, right? So I'm looking at 3 right here, and I want to find an APV value based on Ad Fuller. So this is a statistical analysis of at least less than, or not least, but underneath 0.05 to understand that this data is stationary. And if it is, we can go ahead and proceed forward and do our analysis. So I'm going to do 2 time series models right here sequentially. So I have the ARIMA model, and then I have S-ARIMA, which is just a seasonal version of ARIMA. So ARIMA is auto-integrated moving average, and S-ARIMA is seasonal auto-integrated moving average. Okay, so we have 2 models, and we're going to test the performance of both based on this data set that I just showed you. So the change in air temperature, and they have all these different sensors around New York City. So if you go to this website, it's kind of cool. I'm trying to get more data from here, but City of New York data sets, and you have all kinds of different things you can look at. So I just discovered this kind of recently, probably a month ago. Wait, why is it doing that? Sorry. City of New York, OpenAI, and then you can search for whatever data you want, time series. That's what we're looking at here. But they have all kinds of things, right? So here we have 21 results, air quality, NYC Gov, web analytics, bond issuances for the city of New York. And over here, if you go on the right, or in the left, I'm sorry, business and city government. So you have all kinds of filters that you can apply, and you can look at some pretty cool data sets. So let's go over here and see what's happening. Okay, so the ARIMA and the S-ARIMA are still loading. And again, like we had millions of records, it wouldn't even load into Excel. I'm just taking the first 50,000. I think the data is pretty normally distributed, so we can take a small subset of the entire population. We don't need every single record to do our analysis, because when we take a subset, it should be representative of the population, right? So if you have data that's very random or very unusual or bizarre, you might have to do the analysis on the entire data set, right? In this example, we're just looking at 50,000 records, and that should be sufficient to make a prediction about the whole population, right? We're just taking a small population. And this is very popular in statistics. Usually you don't measure the entire population. It's too time consuming, it's too complicated, and really doesn't add any value, right? If you can get just a tiny % more accuracy, but it takes you several days to do the analysis, is that really a value add? It's probably not, right? It's probably a waste of your time if you're getting very close approximate results and you spend maybe 15, 20 minutes. Let me see the video. I'm into this video now. What's the time? 8 minutes. If you do everything in 20 minutes, then you get your results, which are pretty close, and pretty close is good enough. Then you're done, right? You don't have to get every single decimal place of precision, right? That's how these things work. So still running here, a bit slow. That's fine. We'll just deal with it. We'll stick with it. We'll deal. Okay, and then I'm going to go ahead, after the analysis is done, I'm going to plot the results just so we can see visually what's happening. So I always say in all my videos, a picture is worth 1,000 words, right? If you do the analysis and you get some results and you get numerics, you get numbers, and you get an output, spit out, that's okay. That's a good start. But how do you interpret that? How do you visualize that? How do you share that with your stakeholders? How do you interpret the results? That's really a whole nother concept, right? Just to get the results and say, okay, here we go, this is it, and it's done. That's really insufficient. Like, that's just the beginning of the whole project here. Like, you have to take it right to the end. You start with the results. That's what we're getting right now. But then you have to create some type of visual representation of the results, and then you have to interpret that yourself, and then you have to describe that to your stakeholders or whoever you're working with, whoever is paying you, whoever you're doing the analysis for. Unless it's just for yourself, like you usually have some business partner or some kind of executive committee or some type of like senior people that are going to review the results, right, and make a decision based on the work that you've done. So we're trying to get the results right now. It's a little bit laggy right here. I thought it'd be a little bit faster, but that's still fine. That's fine. It's fine. Okay. And I can run in Excel. I think you just saw that. I think I just kind of like showcase the next step here. So you can see S-ARIMA is negative 0.8951 and ARIMA score is 0.0273. I just ran the next results. And you can see right here, the ARIMA forecast is the red line. The ARIMA basically does nothing whatsoever. The S-ARIMA is trying to do a good job. This is seasonal, right? Because again, we're looking at temperatures based on sensors that are collecting information located all around New York City, right? So this is definitely seasonal. You have ups and downs, you have fluctuations. The red line is really the ARIMA analysis. It's totally underperforming. It says it's flat. You know, the temperature in New York City is not flat every single day of the year, right? And it goes up and down, especially throughout the seasons. So S-ARIMA is kind of capturing the nuances here, but if you zoom in a little bit, I love these Plotly charts because you can zoom in and zoom out. We're really missing the point quite a bit here. So you have the flat red line, that's useless. The black line is the actual number, and the S-ARIMA is the forecasted number, but the forecast is a little bit close, but not really close. If you go back here, you can see the S-ARIMA is kind of like making some determination about what the weather is, but it can't figure it out. And the ARIMA score is close to 0. That's why it's flat, right? So it's not doing anything whatsoever. So I'm going to go ahead and create a scenario where I can loop through a whole bunch of models and see which model can perform the best. So we tried this one and this one. They both came up short. I want to try a third called Holt Winters. I want to try Naive Bayes, XGBoost, which is more of a regression type of model. XGBoost actually offers both regression and classification, so it's kind of unique. Random Forest does the same thing. They have regression and they have classification. LSTM is long short-term memory, so it's another time series model. TensorFlow and PyTorch are deep learning models, so it's more trained on how the human brain performs and how a human would learn whatever scenario they are exposed to and process the information, right? So we have a bunch of models. This is very primitive, very basic. This is a little bit better based on seasonality fluctuations. Holt Winters is, I don't even know what this is per se. This just came up on my radar recently. I haven't even really studied this much. Maybe I came across it a while back. Holt Winters, let me see, exponential smoothing. Seasonal method or exponential smoothing, time series forecasting. Okay, so here's one article. Template for seasonal forecasting. Okay, so it's probably similar to this. This is a seasonal forecasting model. This is seasonal. It sounds like Naive Bayes. It's actually very basic. It really just says whatever happened yesterday is going to happen today. So very, very basic, but it does make slight adjustments and fluctuations because yes, they can't be exactly the same as today. Otherwise, again, you would see the same result you saw over here, like the flat line, right? This red dotted line, nothing changes. You can tell in New York City, in the middle of summer, maybe yesterday was 85 degrees, maybe tomorrow will be 85 degrees. But between different seasons over a long time period, we have September until October, the temperature is not going to be flat. It's going to be fluctuating. It's going to be moving around, right? So there has to be some movement. So Naive Bayes is going to make assumptions that yesterday was pretty similar to today, but it's going to make a little adjustment based on whatever changed yesterday, right? So it's not going to be a huge change, but it should understand the change and mimic the change pretty accurately. XGBoost is looking at a whole bunch of different sort of like different random forest outcomes. It looks a little bit like a random forest decision tree, but it actually takes one model. It's called an ensemble model. It takes one model and does the train testing, looks at the outcome, takes the results, transfers that to another model, does the train testing, looks at the outcome, takes that, transfers that to another model, does the train testing, looks at the output, and takes that to another model. So it's a whole bunch of models that you're running one after another, and you're boosting this process over and over and over, so it gets better and better and more proficient over time. The LSTM is long short-term memory, so long-term memory is preserved. You don't forget what happened in the past, but the short-term memory is more important and has more influence on what's going to happen next, right? So what happened 5 days ago is probably more important to what's going to happen tomorrow rather than what happened 5 months ago or 5 years ago, right? So the short-term memory is more influential and more important, but the long-term memory is still preserved and it doesn't go away. And these two, TensorFlow and PyTorch, are more deep learning models. If I Google that just real quick, let me look at this thing. This is more like a human being would learn. TensorFlow model. Let me just look, see what it says. Keras model built with Tensor. Maybe this thing. So machine learning in the browser, models and layers. It looks at a bunch of deep layers and deep learning, and a lot of data is collected. The model is trained. A lot of different operational layers are applied, and then the model makes a decision based on a bunch of inputs. Right? You have a final output, and PyTorch is kind of the same different thing. Same different thing. Is it actually a thing? Kind of the same thing. PyTorch is kind of the same thing. Like basically like a human being would learn and I get trained and then make decisions, right? So building PyTorch, let me go down here. Sometimes the first Google link is not the best. How to build neural networks. So neural network, maybe this is it. Let's see what it says here. Oh, it just gives coding examples. Let me try this. What is? Let me try this. What is? Full-featured framework for building deep learning models. Yep, that's what I said. Each machine learning model is commonly used in applications like image recognition, language processing. It's relatively easy for most machine learning developers to learn and to use. So let me look at the differences here. TensorFlow uses static computational graphs, which are fixed once defined, and PyTorch offers dynamic computational graphs allowing for on-the-fly modifications during training. This makes it ideal for projects requiring adaptable architectures. Okay, so I think we got that. So let me see how the process is working here. Okay, so I think the model process is almost done. And again, we're looping over a bunch of different models, right? So I put all these models into a list. I'm looping through the items in the list. So we have ARIMA, SARIMA, Bolt Winters, Naive, Bayes, XGBoost, LSTM, TensorFlow, and PyTorch, right? And then here are all the different models right here, ARIMA and SARIMA right here. And we have the seasonal ordering. And down here we have Naive Bayes, XGBoost, and then LSTM, long short-term memory. And we're calculating the R squared for each one, right? Then we get down to TensorFlow, that's down here, and finally PyTorch, and we get the final results down here. So this is the R squared for all the models here. So 0.97, 0.96, 0.93, and I'm going to run this just to get the visual representation of the outcome here. So this time series has strong autocorrelation or low volatility. The recent value is really a good proxy for the next value. That's why we're getting good R squared for a naive Bayes. TensorFlow is pretty high too. XGBoost is pretty high. LSTM is decent. But again, naive Bayes is really the best. Over here we have ARIMA kind of underperforming. Bolt Winters, SARIMA, and PyTorch really underperforming. I'm a little bit surprised. I thought PyTorch would be better, but TensorFlow makes sense, and then naive Bayes totally makes sense here. So let me go ahead and make a prediction here with this chart. Okay, and we can see plotting what is going to happen in the next 24 hours. And if I zoom in here, you can see the results here. So you can see the up and down of the temperature fluctuations. So this right here is probably evening time, and the peaks are daytime. So you have peaks and valleys, daytime and evening time, right? So that is pretty repeatable and pretty predictable. And you can see the temperature is dipping down in October, and it's a little bit higher in June and July, right? So that totally makes sense. And then if we go down here and hit Control Enter, I can refresh this cell, and we get the naive Bayes forecast versus the actual. And if I zoom in here, you can see there's a very close result here between the actual and the naive Bayes, right? So if I zoom in a little bit more, you can see that the model actually predicted what the actual value was going to be very closely, almost perfect, right? So if I zoom in, the red line is the model line, and the blue line is the actual forecast line. And you can tell, based on the outcome over here, this is 0.97. So 97% of the time, the model is going to make accurate predictions. So the naive Bayes model is really the best time series model of all these, right? So you have naive Bayes, TensorFlow, XGBoost, LSTM, ARIMA, Bolt Winters, SARIMA, and PyTorch, and you can see the R squared of each model. So this model is clearly the best. So the whole point of this video is to loop through a bunch of time series models, and then we get kind of lazy, right? You just have the model, click the button and run it, or hit Control Enter and run the process, and then we get the results. So we don't have to test 1, 2, 3, 4, 5, 6, 7, 8. We don't have to test 8 different models separately and independently. We can test 8 all together in sequence, right? So that's the whole point here. So getting kind of noisy in the background. I'm going to wrap it up for this video. Thanks for your time, and I will share the video and the code with you guys, and I'll see you in the next one. Bye.